This is going to be our 21st lecture on optimal power flow. Here, in the yesterday's class, we discussed about ACOPF and the modeling and everything on ACOPF. I hope the concepts are clear. Now, in this class, we will see about DCOPF. Let us try to model the same equations for the same two-bus problem. So let me just draw the diagram here. So for this two-bus problem, let's say because we have we know from the DC concepts that we ignore the reactive power, we ignore the voltages, voltage magnitudes, so there will be just angle, and we ignore the uh, ignore the resistance on the line. So let me quickly derive the equation for you. So let's say if can anybody volunteer here and tell me what will be the objective function? So let's say the objective is linear. So let me just write it down: F1 Pg1 plus F2 Pg2. Right? Before we go ahead, let me just again write the table here, what all will be the parameters, what all will be the variables, so you can help me with this. So can you tell me what all are the parameters here and what all are the variables here? Anyone? Hello? Am I audible too?
Yes, sir.
Yeah. So can anybody help me with the parameters and variables?
So I think that the variable is Pg1,
Yes.
Pg2,
Yes.
Qg1 and Qg2.
No, we are doing DCOPFs, right? So there is no QG1 and QG2.
Yeah. It's linear.
Yeah, it's linear. So what?
Del 1, del 2.
Yes. So del 1 and del 2 will be the variables. Right. Now, what will be the parameters or the known values? So known values will be PL1, PL2, X12. Do you agree with me on this?
Yes, sir.
So you can observe one thing from here is that the number of variables what was there in ACOPF compared to that, here the variables have reduced drastically and there are now only just 4 variables for 2-bus system. So this makes the problem much simpler. That's why in practice or in practical systems we run DCOPF and not ACOPF, but power flow we run AC power flow. So that will be a different topic, but I'll just give you idea here. So okay, tell me what will be the equality equation, and let's say if we write it for bus 1. What will be the equality equation for bus 1?
The power balance equation in linear form.
Yes, tell me what will be that?
Pg1
Yes.
minus P load 1
Yes.
minus V1.
No, V1 is not there again.
Yeah, Y11.
No, Y is also, yeah, but you can write instead of Y we can write B because it is just reactance. So you can write
Yeah,
X12 or B12.
yeah,
So generally we write B12 delta 1 minus delta 2 equal to 0. So we saw in the derivation that Pi is equal to delta Ij into Bij, where delta Ij is nothing but delta I minus delta J. So this we saw in the derivation, if you remember. Right? So this will be the equation. Will there be any other equality equation? Anybody? Will there be any other equation?
for bus 1 there is no equation.
Yes.
For bus 2.
Okay, bus 2. Yes, good. So what will be the equation for bus 2?
BG2
Yes.
minus B load 2
Yes.
minus B21
Yes.
multiplied by del 2 minus del 1 equal 0.
Good, good. Yes, this is going to be. And anyway, because it is purely reactive, there is no complication. So B12 and B21 are going to be the same value. So there is no difference in that. Okay, so these are the two equality equations. Now, is there any other equality equation which is going to be there? Or if not, then let us go for inequality equation. Do you see any other equality equation here?
No more equality equation.
Okay, good, good. Yes. So let me tell me what will be the inequality equations now. What will be the inequality equations?
The limit of BG1 and BG2?
Yes. So PG1
also delta.
yes.
And line flow limit.
Yes. How to write the line flow limit equation?
Upper limit will be the limit that S whatever
Let's say yeah.
S12
Yeah,
maximum.
it's okay. Because here we will write P12 because there is no reactive power, so P12 it will be. Only real power will be there.
And lower will be minus P12.
Yes, but what will be the expression? Oh.
Sir, B12 into delta 1 minus delta 2.
Yes, so the power flow is going to be this one. So power flow is going to be this one, P12 delta 1 minus delta 2. So this is the value of power flow. So this becomes very simple in DC OPF to visualize, but it is difficult to visualize in AC OPF. You said the same thing, right? So this expression, what I said, this is nothing but the power flow on line 1, 2. Right? Will there be any other equation here or it is done?
I think it's done.
It is done, sir.
Yeah, it's done. It's done. There will not be any other equation. Okay, now what we'll do, this is a very simple linear problem. I hope everybody can see that it is very simple. The example which I gave in the quiz, It is like that only. It is very simple. Now let me give you the data. Can you calculate the value for me? Can you calculate the the values for me? So let me give you the values. Let me go to the next screen. Yeah, let me go for here. So basically, let's say this is the generator. You have to calculate this value. So let's assume that the uh, generator can generate at 10 rupees per megawatt. It's a superficial case. The second generator can generate 20 rupees per megawatt, right? Now I'm giving you the load value. Let's say the load value is 100 megawatt at the bus 1. At bus 2 it is 200 megawatt. Okay, now the generation limits, right? So let's assume the line reactance is 0.01 per unit. Okay, now generation range will be required, right? So that is missing here. So let's assume the PG1 so the PG1 minimum limit both is 0. Maximum, let's assume it is 400 megawatt, and this is also 400 megawatt, right? We will do 3-4 problems today and let us solve that, and let us try to understand the generation values and how do you calculate these OPF without running optimization. So you just need to apply your mind and visualize it, and you can solve this problem. So in this condition, let's say I'll call it case 1. What is the value of PG1, PG2, and let's assume delta 1 as 0, so delta 2. Tell me these values. What will be these values? Without running optimization, just visualize it and tell me. And assume one more data I missed. Let's assume the line limits are minus 500 plus 500 megawatts. Right. Now tell me what will be the values of PG1, PG2 and delta 2. Anyone try to wants to try it with me? Can help me solving this? Anybody has idea how to start here? How to start solving
Sir, PG1 300 and PG2 0.
Why? Why do you say so?
I take this case. If the generator 1 generate all power, all amount of power.
But why do you consider generator 1 first? Why not generator 2 first?
Because cheaper.
Yes. Okay. Good. So I hope everybody is able to understand it. You have to look for the cheapest generator first. So the first generator is the cheapest. So let us assume that all the power generation is going to be generated by the generator 1. So let's say generator 1 generates 300, right? And generator 2, because 300, why? Because 300, because 100 is required at bus 1 and 200 is required as bus 2, right? So total load is 300. If let's say generator 1 generates total 300, and then generator 2 will be 0 because 300 load is required. Now you see all these three constraints one by one. So this constraint, let's say I call this 1, 2 and 3. So let's talk about first constraint here. So first constraint is satisfied, right? Second constraint, it is also satisfied. Third constraint, what will be the power flow?
200, sir.
Why 200?
200 megawatt.
Why 200? Because the load is there at bus 2 at 200 megawatt,
100.
Yeah.
and at because this is a DC OPF, here we ignore the resistances, therefore we ignore the losses. So therefore whatever is the power that will automatically go to the second bus, so that means the third power flow is also 200, so that is also satisfied. With this you can easily calculate, B12 is 0.01, delta 1 is 0, so this is 0 minus delta 2 is equal to 200. So can anybody quickly, anyway this 200 will be not there because you have to write everything in per unit. So let's say 100 MVA is the per unit, so you have to write just 2 here. So what will be the value of delta 2? All the process and power system, from the basics that every time the power system is always calculated in per units. So what will be the value of delta 2? Can you calculate from here and tell me the value of delta 2? Again, one mistake I did. This is x12, so this is not b12, this is x12. So basically this will be, wait, this will be x12, which is nothing but 0.01.
Equal minus 2.
Delta 2 equal to minus
2.
No, it will multiply this 0.01 will go here, it will be minus 0.02. Right,
The
and
value will be 1
Why
over
2,
x.
not 200?
yeah,
The
200.
value
not
of
2.
nee, this power flow you have to keep every time in per units. So basically that's why I assumed that the base MVA is 100, so just divide it by 100 here. So that's why we always calculate them in per units. So basically, so it will be 200 divided by 100, which will be 2. We always
say, I think the value of b is 1 over x12.
so that's why it is 1 by x12. So basically this value which I gave, this is x12, this is not b. So basically it will be b12 will be 100.
Yeah.
So that's why if you divide b12 here, it will be 0.02. Is it clear?
Yeah, it's clear.
Okay, good. So right, now we have satisfied all three equations, we got all three ticks. So basically we can say that this is the optimal solution. You do not have to run optimization because the objective function is cost minimization. And you know that when the objective is cost minimization, we want to minimize the cost. And minimize the cost, how can you minimize the cost? Whenever you schedule the cheapest generator first, and then you gradually keep on increasing the generator, right? Now let us change something here. Now let us do the case 2. Case 2 here, what I am doing is basically right now generator 1 has an upper limit of 400. Instead of that, let me make it 200. Now can you tell me what will be the optimal solution? Case 2.
PG1 200 and PG2 100.
What will be the value of delta 2?
minus 0.01.
Delta 2 equal to 100. Yes, 0 minus 0.01. Now, so do you get the point that how do we run the optimization? Means you how do you get the solution for a small problem without running optimization? You do not need to run optimization. Only when the problem is very big and it is difficult to visualize, then only you go for optimization. Otherwise you go for regular thing. Now now let us see what will be the lambda. Basically, I was also discussing in economic dispatch that there is a lambda which is the dual variable corresponding to the power balance equation. Corresponding to the power balance equation, which is sum of generation equal to demand. Here this lambda, instead of power generation, here that lambda is basically for individual bus. So can you guess? Let's go back to the case 1. What will be the lambda? Lambda is basically the dual for the power balance equation for the first bus and the second bus. So here if I write the power balance equation of the first bus, it will be like Pg1 let me write P12, and the second equation will be Pg2 minus PL2 plus P12, because that will be reverse, right? It is delta 2 minus delta 1. Let's assume P12 is just B12 and delta 1 minus delta 2. Right. Now in this equation, the dual for this, or dual variable for this equality equation, is going to be the lambda. So there will be, this will be lambda 1, this will be lambda 2. Now when you see lambda 1 and lambda 2, what will be the value? Can you guess in the case 1? Let me just quickly erase and let us try to make it visualize to all of you that how we calculate the value of lambda 1 and lambda 2 is basically, if let's say we form the Lagrange function, it will be the objective function, which is a function of Pg1 and Pg2, plus lambda 1, where this will be the power balance equation for bus 1, plus lambda 2, which will be power balance equation for bus 2, right? And there will be some other equations. Now lambda is basically, if you see the dimension, let's take the dimension. So the dimension of F, what is the dimension of F? F is a cost, so it is just in rupees, right? So F is in rupees, then L is also in rupees, the Lagrange function, right? And just ignore this. Let's assume that this term is not there. Let's assume that this is not there and there is no other term. Then lambda 1 will be equal to partial derivative of dl by dpg1, right? Now when you see this, what will be the dimension here? Dimension will be, can anybody guess what will be the dimension? So dimension will be, because rupees is the dimension for the L, and Pg1 is in megawatts, so it is rupees per megawatt. Right? Now when you see that the dimension of lambda 1 is rupees per megawatt, that means this lambda 1 is, you can correlate it in terms of price. Right? So in the next semester, we will be seeing this logic that how this lambda 1 is going to be a price, and because we will be studying power system deregulation, so there we are going to see more detail of this topic. But just wanted to give you a flavor here that this is a price, rupees per megawatt. Right? Now, because we know that at the first bus here the power generation was 300 megawatt, so Pg1 was generating 300 megawatt. So here you know that the first generator is generating 300 megawatt, second generator is generating 0 megawatt. So what is the cost which is required by the generator? So generator is basically generating, or rather let me make it even more simpler for all of you, that delta L by delta Pg1, you can also write it in the sense that instead of taking this partial, if let's say if I am doing this for a small generation change, that means it will be delta not partial derivative, right? Now if let's say if I change the load by 1 megawatt at the bus 1 and the bus 2, whatever is the change in the load, and the change in the load will lead to some generation change, and that change will be the price. This is the way we calculate the price without running the optimization. Eventually you will get the same value from optimization, but I'm just giving you an idea. So let's say if I want to calculate lambda 1, so what I will do, because lambda 1 I have to calculate, so what I will do, I'll add 1 megawatt or a small value of load at bus 1, and then I will run the rerun the optimization, and then we will get the value of price change. So let's assume this load at bus 1 I have increased from 100 to 101. Let's assume I have increased a very small load which is 1 megawatt. Then this megawatt will be generated by which generator? Can you tell me this? Now instead of this 100 megawatt, right now the load is 101 megawatt, bus 2 it is 200 megawatt. Then what will be the solution, optimal solution? Anyone? It will be 301 megawatt, right? So, and the generator wants 10 rupees. So it will be 301 into 10, right? And when it was 100, it was 300 into 10, right? Divided by what is the change in the load what you did, or the change in the generation what has happened, it is of 1 megawatt. So eventually you can get this value as 10. So basically the lambda 1 will be 10 rupees per megawatt. And if you run the optimization, you will get the same value. Do you agree with me on this?
Yes, sir.
Now what we'll do is basically if you want to calculate lambda 2, let's say we increase the load at, you can also write load here, it will make similar sense. So let's say if we increase, keep the load at bus 1 as 100. Now increase the load at bus 2 by 1 megawatt or very small value. Now who will give this generation? So obviously you can see here in this condition, the first bus is going to give that generation. So it will be 301 into 10 minus 300 into 10 by 1, because you have increased the load by 1 megawatt. Eventually this will also be 10 rupees per megawatt. Right? So basically what is happening here is you have to change the load at each bus, and you have to see the change in the objective function, whatever is the change in the objective function. So let's say you can also write here change in objective function. I can also write as delta F with respect to change in the load. So lambda is nothing but it is rupees per megawatt. It is the price what is being paid by the loads for their consumption, and the same price will be paid to the generator for their generation. So here you can see that total load is 300 megawatt. So everyone will pay at 10 rupees because lambda 1 is also 10. Lambda 2 is also 10. So total they will be paying at 300 into 10, which will be 3000 rupees. And then generator will get what generator is expecting, he is also expecting 300 because it is generating, and he wants 10 rupees. So he will be total requesting for 3000 rupees, and obviously loads are paying 3000. So eventually the transaction is balanced. So whatever is paid by the loads, the same is being given to the generators. So 3000 equal to 3000, it is balanced. Right? So this is the way we calculate the prices. I'll not go more because today, or rather I can take one example. If you guys are here, I can take one example. The other example, when the generation limit was 200, then what was the generation schedule and who will give for whom. Let us quickly see that case again and then understand the value of lambda.
Sir,
Yes, please.
I have a question.
Yes,
I have a
please.
question.
Yes.
If the load change from 100 by 101, if the load in both one
Yes.
being 101,
Yes.
so if can the generator generate 401,
Yes.
what the scenario happens?
Good question. Okay, that's what I'm going to show you just now. So, okay. So this was the case. Let me just quickly draw it. We saw PG1 has limit from 0 to 200. I'm changing it 0 to 400, and this is generating at 10 rupees per megawatt. It is generating at 20 rupees per megawatt. Here the load is 100, here the load is 200. Ignore the line limit for a while. Now we saw that when this situation is there, that means PG1 will be generating 200. You have already answered this question before. PG2 will be generating 100. Now delta 2 will be minus 0.01. This you have already told before, right? And everything is same. Now what will be the lambda 1 and lambda 2? So lambda 1 is the change in objective function, cost in the objective function by the change in load at bus 1. Right? So now the situation here is, if the load at bus 1 increases by 1 megawatt, obviously generator 1 is already hitting its upper limit. So generator 1 cannot give that extra power. So who will give that extra power? Adam, can you answer this? Who will give this extra power?
Generator 2, sir.
Yes, good. So the generator 2 will give. So what will happen? The total cost change will be what? Generator 1 will be generating at 200 megawatt into 10 because he wants 10 rupees. Plus now because of this 1 megawatt increase, total generator 2 will be generating 101 into 20, right? Now initially what was the situation? Initially was 200 into 10 plus plus 100 into 20, and because this is the total objective function after adding 1 megawatt and before adding 1 megawatt, and the load change is 1 megawatt. So this value will be how much? Can anybody quickly calculate and tell me? So this will go away, this will go away, and this will be 20. So the price at the bus 1 will be 20 rupees per megawatt. So the load at bus 1 will be paying at 20 rupees per megawatt. Now let us see at bus 2. It is clear, right? Now I think I answered your question. If the generator is not able to increase, then the power will come from the neighboring bus, or from wherever bus it can come. Right. So now let us see about lambda 2. Can anybody help me? What if, let's say, initially the situation was 200 into 10. This will remain constant. Now we are increasing 1 megawatt. So the first bus is also going to be constant. First bus is going to be 200 into 10. We are increasing 1 megawatt. Obviously the first this 1 megawatt I am increasing at the second bus. Here I am increasing 1. And we know that the second bus generator can only generate because the first generator has already reached its maximum limit. So the next generator will come from the second bus. So it will be 101 into 20 and this will be 1. Eventually if you calculate it, it will be 20 rupees per megawatt. Any doubts here? Any concern here?
Yes, concern.
Yes, please.
In the price.
Yes.
The generator 1 give us 200.
Okay.
For 20 rupees per megawatt.
Yes.
But the generator 2 give us only 1 megawatt in the same price.
Yes.
Do you get my point?
You mean to say that the generator 1 is generating 10 rupees at 200 megawatt, means 200 megawatt at 10 rupees per megawatt?
Yeah.
And generator 2 is generating at 20. Even then the bus 1 is paying 20 rupees per megawatt.
I think the price will be less in generator 2.
No, it will be this only. So okay, let me try to make it even simpler from you. So basically what happens, this again I'm just giving you a small idea here. This we are going to see in detail in the next semester when we have this power system deregulation course. So the idea here is that the first bus, I'll just give you a quick idea. First bus, because the generator is already generating at its maximum limit, what happens here is that the generator loses the control of setting the price. So this might be very difficult to visualize at this moment, but simply you can visualize here that a generator, let's say, talk about in power flows, when you have a reactive power, in power flows you keep a reactive power limits, right? So whenever you say that the generator is within the reactive power limits, then you say the generator is a PV bus, right? and as soon as the generator hits its limit or reactive power limit, then you say it cannot control the reactive power anymore, and you say that this generator has become a PQ bus, or that bus has become a PQ bus. Do you agree with me on this from the conventional power flow concept?
Yeah, I agree.
Yeah, so in the same sense, here also what we do here in this, the concept of inequality is always same, that whenever generator reaches its limit and it is means it is operating at its upper limit or lower limit, in this case the generator loses the option to keep the price at 10 rupees, and then the price will be decided by the other generators, not this generator. Right? Do you agree on this?
Yeah, I agree.
So this is the same logic here, and eventually what is happening, if you see here, that total loads are paying, the bus 1 load is 100, so he is also paying at 20, so he is paying total 2000 rupees. Bus 2 is actually paying sorry, let me write it loads here. Wait, loads. So load 1 is paying 2000 rupees. Bus 1 and bus 2. So bus 1 is paying also 2000, and bus 2 is paying actually 4000, because 20 into 200, so it will be 4000. But how much generators are getting now? They are also getting, the generator 1 is generating 200 into 20, the generator will get 4000, and the bus 2 generator was paying for generating 100 megawatt at 20 rupees, so he will be getting 2000 rupees, right? So eventually the balance is there, so total loads are paying 6000 and total generators are getting paid at 6000, so that transaction is balanced. But the issue here is that the generator 1 was actually needing only 2000 rupees, right? Because he was generating 200 megawatt and he wants just 10 rupees per megawatt. But here you can see here that he is getting a profit of 2000 rupees. Do you see the point, that he is getting a profit of 2000 rupees? So this profit generally all the generators make when they reach their limit. But it is not always true, they can make loss also, because they do not have control on the prices. So the prices are decided by the neighboring generators. It can be cheaper or it can be costlier, whatever it is, it will decide the price. Right, so I'll not take more. I'll stop here, and we can discuss this more after the midterm exam. We can discuss this in detail in the midterm exam and after the midterm exam. Any questions as of now?